Hello everyone. The topic for today's lecture is economic and surface finish considerations in machining. In today's lecture, we will talk about machinability. What is machinability? And what are the parameters affecting machinability? Then we will talk about achievable tolerances and surface finish in traditional machining operations, including turning, boring, drilling, milling, broaching, and some other traditional machining operations. Then we will talk about different methods of selection of cutting conditions, including the feed and also cutting speed, on the basis of economic considerations. And this is followed by a brief discussion of design considerations in order to lower the cost of machining. Well, what is the definition for machinability? Machinability is defined as relative ease with which a material can be machined. Of course, when we are making use of appropriate machining process or machine tool, cutting conditions, as well as cutting tools, because all this play a role in the success of a machining process. Well, the mechanical and also physical properties of the material will play a role in the success of a machining process, and this will affect machinability. For so many applications in engineering, we are interested in the presence of high strength and hardness of the material. And for doing this, often we do add some alloying elements to the material to improve its mechanical and physical properties. By doing this, we may be able to enhance the strength of the material. However, we should be aware that this will have a negative impact on the machinability. That is, as the material is stronger and harder, then its machinability will be lower. It is harder to machine a stronger material than a softer material. So we may need to actually compromise between these two, and those are machinability and the strength and hardness of the material. And as I said, the type of the machining operation will have an impact on the success of the machining operation, and also it will affect machinability. That is, the machinability of the same material could be different when it is subjected to turning, or say to broaching, or some other types of machining operations. The type of the cutting tool we are using, and also the selection of the cutting conditions will have an impact on deciding machinability. And we will discuss all this in today's lecture. Well, in this slide, a number of factors are listed as machinability criteria in production, starting with tool life. When machinability is high, it is easier to cut the material, and as a result, our cutting tool will last longer, lowering the cost of tooling. And when we are dealing with a machinable material or process, then the resulting forces and power will be less. Reason, there is a risk, a need for less machining forces and power requirements in order to cut the material because of lower strength of the material. And also, when we are dealing with a machinable material, it's easier to achieve a better surface finish. When machinability is low, then the resultant surface finish will not be so good. We may require to add additional operations in order to improve the surface finish, and this will increase the cost of production. However, in machinable materials, by making use of the same process, same cutting conditions, we may achieve a better surface finish, and this may eliminate the need for applying an additional machining process to improve the surface finish. And also the ease of chip disposal is important. Sometimes chip disposal becomes a barrier against say productivity. So for a material which has got a high machinability, it is easy to actually dispose the chip and remove the material from the machine and also the work environment. Well, when we talk about machinability, indeed what we are doing is to compare the ease of machining of one material with other ones. And in order to do that, a number of tests can be performed to actually rank the materials according to their machinability. And the relative performance is expressed in terms of machinability rating, or MR. MR represents machinability rating, and often when we are going to say compare the machinability of different materials, a material is chosen as the base material and its machinability is rated as 1 or 100%. All the other materials, the machinability of all the other materials are rated on the basis of, or in comparison with the base material. If the machinability of a test material is greater than 1, it means that it has got a better machinability than the base material. And of course, when its MR is less than 1, it means that its machinability is lower. Well, now let's take a look at this example problem to see how we can rate different types of materials on the basis of their machinability. Well, in this example it says that a number of tests are conducted on two different work materials under identical cutting conditions, varying only speed in the test procedure. The first material that is considered as the base material yields a Taylor tool life equation as given here. We are familiar with Taylor's tool life equation from the previous lecture when we did talk about Taylor's equation. In Taylor's equation, we know that V represents cutting speed, T is the tool life. This exponent, which is referred to say Taylor's tool life exponent, depends on the quality of the cutting tool material, and it is represented by lowercase n. For this given example, it is 0.28, and this is equal to a constant value for a given material and operation, that is C. For this say base material, the values of N and C are given, and then we are subjecting this same material, a different material, to a similar operation, and for the second material, which is the test material, the values of N and C are different. N is very close to what we had before and C is different. Well, now the problem is asking us to determine the machinability rating of the test material, which is the second material, with respect to the base material, using the cutting speed that provides a 60-minute tool life. As you know, this T is representing the tool life. So we want to rate the machinability of the second material with respect to the base material, and the cutting speed giving us a tool life of 60 minutes can be written just like this here. In order to do this problem, we've got to make use of the Taylor's tool life equation given down here, right here, and we can solve the equation for V, which results in this, and then what is given for the base material in the statement of the problem is to be substituted into this equation. So C is the value of C and N are given, and we know that we are going to compute a cutting speed giving us a tool life of 60 minutes. So 60 sits in the place of T. So for the base material, a cutting speed giving us a tool life of 60 minutes is computed now. That is equal to 111 meters per minute. We can do the same for the second material or the test material. By substituting the values of C and also N in this equation, then we can compute the cutting speed giving us a tool life of 60 minutes for the say test material, and this comes to 146 meters per minute. Now when we want to rate the machinability of this test material with respect to the base material, all we need to do is to divide this value, that is the cutting speed of the test material for a tool life of 60 minutes, by cutting speed of the base material for a tool life of 60 minutes. And this is down here, which will give us a machinability rating for the test material that is equal to 1.31 or 131%. And what this means is that the test material, the machinability of the test material is greater than the base material. So in order to rate the machinability of the test material in this given example, what we did take into consideration was the tool life criterion, and this is the most common criterion that is taken into consideration in assessing the machinability of different types of materials. Well, in this slide we can see different types of tests that can be performed in order to assess the machinability of a material, and those include tool life, tool wear, cutting forces, power requirements, the temperature of cutting between the cutting tool and also the chip, and also the rate of material removal. Each one of these could be taken into consideration in the determination of machinability of different materials. However, as we can see up here, tool life is the most common test that is used in order to rate the machinability of different materials, and that was the case in the example that we considered in the previous slide. Well, now let's talk about mechanical properties of materials when deciding machinability. Well, mechanical properties of the materials include hardness of the material, and of course we know that when hardness is high, then abrasive wear increases, and this will result in a shorter tool life, increasing the cost of tooling. And as I mentioned before, when we are improving hardness and also strength of the material, we are decreasing machinability, and then we are increasing the cost of manufacturing accordingly. When we talk about hardness of the steels, for example, we know that as carbon content increases, the strength and also hardness of the material will increase, and this will reduce machining performance. So selection of a really hard material is no good when it comes to machining. And strength. High strength means higher cutting forces, of course, and that means a specific energy and cutting temperature will be higher. Well, when we talk about strength of the material, we should also know that say some alloying elements which enhance the strength of the material include chromium, molybdenum, and tungsten. These alloying elements increase the strength of the material as they form carbides in steel, and this will increase tool wear and as a result will reduce machinability. Some other alloying elements including manganese and nickel will also add strength and toughness, strength and toughness of the steel, and these will also reduce machinability. So if we want to choose a material with high machinability, we've got to avoid high contents of chromium, molybdenum, tungsten, manganese, and also nickel. And when it comes to ductility, we should also know that high ductility means that there is a higher possibility of tearing of the material when cutting tool is taking the cut and it's removing the chip from the material. Generally for ductile materials, disposal of the chip is more difficult, and this will result in deformation of the surface of the material and will produce in a poor surface finish. Some other alloying elements including lead, sulfur, and phosphorus will reduce the coefficient of friction between the tool and also the chip, and these will reduce forces and temperature and also the possibility of creation of build-up edge, and this will result in better tool life and also better surface finish. So these are some considerations which ought to be taken into consideration when we are choosing the material. Let's take a look at this slide here. In this slide we see a table which is rating different types of materials on the left against hardness of the material given in BHN, Brinell hardness number, and also machinability rating. And in this table, as we can see, the base material is chosen as steel B1112. Its hardness value is given and its rating is 1. And the machinability of all the other materials in this table are rated on the basis of the machinability of the base metal. So B1112 steel is often used as the base metal because, and it is having a machinability rating of 1. Well, taking a look at this table, we can see that there are different types of steels and alloy steels, stainless steels, tool steels, cast irons, medium hardness steels, as well as super alloys, titanium alloys, aluminum alloys, and some other types of alloys including copper, brass, and bronze. Of all these, there are just a few of the materials with a higher machinability rating, and those include this steel B1113 with a machinability rating of 1.35, free machining steels with a machinability rating of 1.5, as well as alloys of aluminium. Look at this one. The machinability rating of this type of aluminium is 5, which is a highly machinable material. Well, this table will give us a rough idea on the machinability of different types of materials when it comes to the selection of the material. Of course, it will be less costly and less troublesome when we choose a machinable material for the task of production. Of course, we've got to take into consideration so many other parameters, and only one of them could be machinability. Well, in this slide we can see a number of considerations for tolerances as well as surface roughness when we are machining a material. What are the range of tolerances that can be achieved in a typical machining process? And what surface roughnesses can be achieved in a typical machining process? Indeed, we know that we are in need of defining and utilizing tolerances when we are machining a part, because no machining process is perfect and it is not possible to achieve a precise dimension for a product. Always there is a range that is defined as tolerance, and the part is acceptable as long as it is made to a size which is within the tolerance limits. And when we are assigning tolerances, we should take into consideration that closer tolerances usually mean higher costs. So we should not actually assign a tolerance that is too close and that is very tighter than what is really needed. It should be tight enough in order to perform its function. As we tighten the tolerance, we are increasing the cost of machining. I will give you an example in the next slide about this. And also, when we talk about surface roughness in machining, we should know that there are some parameters affecting the resultant surface finish in a typical machining operations. Those include geometric factors, work material factors, and as well as vibration and rigidity of the machine tool itself. Well, let's take a look at this slide here, which is actually providing us with typical tolerances and surface finish or surface roughness values that can be achieved in traditional machining processes. Well, we can see different types of materials on the left column. In the middle column, we have got typical tolerances that can be achieved from these operations, these processes, and in this column here on the right we have say the surface roughness that can be achieved when we utilize the given machining operation. For example, when we are making use of a lathe for turning operation, then we can achieve a surface roughness of 0.8 micrometer. And the resultant say tolerance or tightness of the tolerance that can be achieved depending on the dimensions of the say cutting workpiece are presented here. When the diameter of the workpiece is less than 25, we can achieve a tight tolerance of 0.025 plus and minus millimeter for the given dimension. As the diameter of the workpiece increases, the gap in the width of the tolerance region also increases. So we end up with a wider tolerance band for the acceptable parts. When we are assigning tolerances and also say surface roughnesses to a given part at the design stage, it's a good idea to take a look at this table in order to know what tolerances and what surface roughnesses are achievable from different machining operations. Generally, we should also consider that when we are making use of an old and worn machine, then variability could be greater than what is given in this table here. And when we utilize newer machine tools, we may achieve closer tolerances and tighter tolerances. But this is just a rough guide what is given in this slide. And the other thing that we need to take into consideration is that if we assign a tolerance that is tighter than what is given in this slide or in this table, it means that we may need to introduce additional machining operations to achieve the assigned tolerance or surface roughness. What is meant by this is that if, for example, we are drilling a hole of 6 millimeter in diameter on a drilling machine, then what is the tolerance that can be achieved is given here, that is plus and minus 0.1 millimeter. This is something that can be achieved, and the surface roughness that can be achieved from this is given here, that is 0.8. Now if for the same hole, a hole of 6 millimeter in diameter, we assign a tolerance that is tighter than this range, say for example 0.025, then what happens? What happens is that it means that once we make the hole by making use of the drilling machine, we cannot achieve the required tolerance. So we may need to introduce an additional reaming operation, this one, providing us with the possibility of achieving the assigned value of the tolerance, that is 0.025. So we need to make the hole first and then apply a reamer on top of that in order to enhance the precision of the drilled hole. Or if for the same hole we assign a surface roughness of 0.4, then it cannot be achieved in the drilling process, and we may need to apply a reamer after drilling in order to improve its surface roughness, indeed to improve the surface finish, which is opposite to what is meant by surface roughness. Surface finish and surface roughness are both used when it comes to surface quality. However, surface roughness means how rough the surface is. Surface finish means how smooth the surface is. So they are both used in industry. Often surface finish is used in the industry rather than surface roughness. However, the instrument that is used in order to measure the quality of the surface is the surface roughness instrument, because it is measuring the roughness of the surface, which is opposite to what is meant by surface finish. Okay, let's move on. If we take a look to a machine surface with unaided eye, what we see is a smooth surface. If it is a flat surface, then we see a straight surface. If it is a round surface, then we see it as a round surface. However, if we take a close look at it by making use of a microscope, we will see something like this, that is representing a really rough surface. It's anything other than a smooth surface, as we can see here. And as you can see, those layers on the top of the surface are actually elongated. Those grains are elongated as a result of applying machining forces in the machining process. And in many cases, we are interested in, say, achieving a better surface finish. Reason are actually aesthetic reasons, or sometimes surface may increase or improve safety. It may lower the friction and also wear depending on surface characteristics. If we are talking about, say, mechanical and physical properties, a high surface finish will actually improve the quality, the mechanical properties and physical properties of the material. And if we are talking about electrical contacts, that is, the surface is going to be used as the surface in providing electrical contact, then flat surfaces or smooth surfaces provide a better contact between the two parts. And also, when it comes to assembly, when surface finish is higher, then we will face fewer problems in the assembly line. So it's always good to improve the surface finish as much as possible. How can we do this? We've got to actually utilize the proper machining parameters, including feed, in order to improve the surface finish as much as possible. And if still we are not achieving the required surface, we may need to introduce additional machining operations, including grinding, lapping, and some other operations that are used in order to improve the surface finish after the machining operation. Okay, let's talk about this slide here. What we see in this slide here is the representation of the surface texture. Well, generally when we talk about the texture of a surface, which is mean the topography and geometric features present on a surface, we are dealing with 4 elements that represent the texture of the surface, and those are shown here in this slide or in this figure. Well, let's begin with roughness. This is what we measure in the lab of this unit when we do the machining task. Indeed, in the lab we produce a surface on the machine, and then we measure the surface roughness of it. And this is exactly what we are doing. As you can see, when cutting tool is taking the cut, the actually surface of the machine, the surface of the workpiece is cut by the tip of the cutting tool, and then some field effects are left on the surface of the, say, workpiece. And if we take a close look at it, as we can see here, a rough surface is produced, and by making use of the surface roughness measurement instrument, we are measuring how rough the produced surface is. So indeed, roughness can be defined as small, finely spaced deviations from the nominal surface, and that is determined by material characteristics and also the process that is used in order to make it, whether we make use of milling operation or turning or any other one. These could be slightly different from one another. Well, another element that is to be discussed is the waviness. If we take a look at this surface here, we notice there is a waviness along the length of it, and this is deviation. This is defined as deviations of much larger spacing compared to roughness, much larger spacing, as we can see here. And this occurs due to deflection of the workpiece and also vibration of the machine tool, and heat treatment of the workpiece may have an impact on this, as well as vibration of the workpiece itself on the machine tool table or in the fixture. All these will play a role in say waviness of the workpiece, and this is something that cannot be observed unless if we take a close look at the surface by making use of a microscope or some instrument that is used in order to be used for this. And then the other say element we discussed here is the lay. That one here, the lay direction, and the pattern of the surface texture that is a result of the motion of the cutting tool on the surface when it was cutting the workpiece. And depending on the type of the machining process, the pattern of the lay is different. In the next slide, I have got different types of patterns that are present that can be seen on say machine surfaces, which is a representation of the motion of the cutting tool to make it. For example, here the motion of the cutting tool has been along this direction, or in this one, as you can see, the cutting tool has moved from the outside diameter going inside, which is used when we are doing the facing operation on a turning machine. Okay, back to the picture, back to the figure that we just had. The other type of the defects that can be observed on a surface are referred to as flaws. As you can see, there is a crack right here, there is a crater up here, and there could be some local defects on the surface here and there, and this actually is a result of imperfection of the material, presence of internal defects in the material which we cannot see it, or the result of the formation of the material when material has been subjected to machining. For example, cracks can be formed as a result of excessive cutting forces that are applied to the workpiece. Okay, that was a brief description of the texture of the surface. Now let's take a look at this slide here, which is actually showing a surface that has been machined. If we take a close look at it, we will see some depressions as well as protrusions that are present in a surface machine, in a machined surface. And the arithmetic average surface roughness can be represented by this equation, taking into consideration the height of the protrusions or the depths of depressions into consideration as the absolute values of the depths of depressions and protrusions into consideration within a predetermined length that is referred to as cutoff lengths. And these lengths, cutoff lengths, should be determined in a way that it does not take waviness of the surface into consideration. So this equation is an equation that is used in order to measure average surface roughness. Well, let's talk about geometric factors that affect a machining process. Indeed, the machining parameters that determine surface geometry are listed here, and those include the type of the machining operation. What type of machining operation is used in order to produce the part? It's milling, turning, say shaping, drilling, or any other type of process will have a different effect on what is produced. The geometry of the cutting tool, the size of the cutting tool, the shape of the cutting tool will also play a role in the resultant surface that is produced, as well as the feed. Of course, feed will have a great impact on the resultant surface finish. And the surface geometry or the surface finish can be measured in terms of ideal surface finish or theoretical surface finish, which could be different from the actual surface finish. Let's explain this in the next slide here. Well, let's take a look at this slide here. In this slide here, the geometry of the cutting tool tip is actually studied. Let's see. Here we see the representation of a typical single edge cutting tool that is used in order to cut the material in typical operations such as, say, for example, turning. And as you can see, the tip of the cutting tool is not sharp. Often it is not sharp, and it has got a nose radius or NR. And then there is an angle right here which is referred to as end cutting edge angle, or ECEA in the short form. And this angle is the angle of separation, the angle of the separation of the workpiece, which is cut right here, from the cutting tool. Okay, now let's take a look at figure A right here. In figure A, on the top we have got a cutting tool which is cutting the material with a sharp cutting edge. It hasn't got a tool nose radius. Its tool nose radius is 0. And compare it with this one, where we have got a large nose radius on the tip of the cutting tool. Feed is the same. Which one of these two is producing a better surface finish? Well, indeed, which one of these two is producing let me take the pen. Let's take a look at the depths of depression from the top from the surface that is produced. Let's take a look at this distance right here and compare it with this. Okay, which one is greater? I didn't do it properly. It's hard to make use of the actually optical pen right here. Anyway, this is a rougher surface. There is no question in that. This is a rougher surface than that one because the distance from the depth of the depression to the top is greater than the one which is shown here. So this is a better surface and this is no good. And this happens because of what? Because of the removal of the tip of the cutting tool from right here, from this point. We have removed it, and this helps in order to improve the surface finish or lower the amount of surface roughness. So what can be concluded is that a larger nose radius will result in a better surface finish or in a lower value of surface roughness. Now let's move on to the one in B. In B we have got the same, in this one we have got the same tool nose radius. However, what is different is the feed. Which one is producing a better surface? The one on the top or the one in the bottom of B? Of course, the lower one is producing a better surface and the one on the top is producing a rougher surface. And what can be concluded from this is that for the same tool nose radius, a lower feed will produce a better surface. And the higher value of feed, a larger feed, will result in a rougher surface. And let's move on to the one in C. In C, what we have got, what is different in the top and bottom figure in C is ECEA angle. Its value in the bottom here it's 0, but in the top it is having a non-zero value. Which one is producing a better surface? Of course, the one at the bottom. And this one is no good. This one, the ones on the top are all producing a rougher surface than the ones sitting at the bottom. In theory, we can say that an ECEA angle of 0 will result in production of a perfect surface. However, in practice, this is not possible. This is not practical, I mean. Reason, there is imperfection in the cutting tool, imperfection in the workpiece material itself, imperfection in the machining process. There is vibration in any machining operation, in any machine tool, and all these actually make it impossible to achieve a perfect surface even if ECEA is equal to 0. However, as it is less, it may result in producing a better surface. The equation given down here, this equation, is an equation that is used in order to relate the theoretical or ideal value of surface roughness, this one, to two parameters, and those are feed, as discussed in this slide, as well as tool nose radius, NR. So in theory we can say that surface roughness or ideal surface roughness is equal to F or feed squared divided by 32 times of tool nose radius. But this is just in theory. In practice, we may achieve a different value for surface roughness. Indeed, the actual value of surface roughness could be worse than what is computed here as the ideal surface roughness. What is the reason for this? Well, the reason is that there are a number of parameters affecting the quality of the surface that are not taken into consideration in this equation, and those include the vibration of the machine tool, the imperfection in the cutting tool in the workpiece, the quality of the workpiece material itself that is not taken into consideration, and all these may result in a surface roughness that is greater than what is computed as the theoretical or ideal value of surface roughness. Okay. One more thing that I need to explain before we move on to the next slide. Just as a conclusion, we can say that well, how can we summarize what we learned in this slide? Number one, with the same feed, a larger nose radius causes the feed marks to be less pronounced, and thus leading to a better surface finish. If the two feeds are compared, right here, if the two feeds are compared with the same nose radius, the larger feed increases the separation between the feed marks, and this will lead to an increase in surface roughness. And eventually, in the very last one, we can just summarize what we learned as a higher ECEA will result in a higher surface roughness, and a zero value of ECEA would result in a perfectly smooth surface. However, imperfections in the tool, in the work material, and the machining process would not allow achieving an ideal finish. Okay, let's move on to this one. As I mentioned in the previous slide, the actual value of surface roughness, RA, could be worse than the ideal value of surface roughness because of the parameters such as vibration of the machine tool and so many other parameters, including the properties of the workpiece material itself, that are not taken into consideration in the equation of the previous slide. This figure here is providing us with a chart. In this chart we have got in the horizontal axis we have got cutting speed increasing from left to right. As we know, as cutting speed increases, the vibration of the machine tool will increase as well. This is actually in this chart here we have got a vertical axis which represents the ratio of actual surface roughness divided by the theoretical surface roughness that we just explained it in the previous slide, and this ratio is defined as RAI, and it's sitting right here in the equation. So if we multiply the value taken out from this table, if we know the type of the material, we make use of the right curve, and then we also make use of the right cutting speed. This will help us in order to take the value of RAI out of this table and multiply it by the computed value of theoretical value of say surface roughness from the previous slide, which result in a good estimation of achieving a good estimation of the actual surface roughness. Let's make use of an example in order to explain this. In this example problem, what it is telling us is that there is a turning operation that is performed on this type of steel, C1008 steel, and this is considered as a ductile steel. What is used is a cutting tool with a nose radius of this much, 1.2 millimeter. Cutting speed, or V, is given equal to 95 meters per minute, and the feed is equal to this much. So we've got F, we've got V, and we've got NR. That is all given. and the type of the material also is given up here, that is a ductile steel. The task is to compute an estimate of the surface roughness, that is actual surface roughness in this operation, or RA. How do we do this? In order to do this, what we need to do is first to compute the value of theoretical surface roughness, that is Ri. First we compute the value of Ri on the basis of the equation we have, and then we make use of the chart in the previous figure, take the value of RAI out of it, multiply the value of Ri by RAI, which will give us an estimate of the actual surface roughness. How do we do this? Well, the equation for surface roughness as we had it in the previous slide, Ri is equal to feet squared divided by 32 times our nose radius, of course. F is given, which is sitting right here, and then this is NR. By doing this, we can compute the value of theoretical or ideal surface roughness, which is equal to this much in micrometers. And then we've got to take the value of RAI from the chart. If we go back to the previous chart for a cutting speed of 95, that is given up here. Let's go back to the previous chart. If cutting speed is 95 for ductile material, which one is ductile material? This one. So the curve representing the relationship between RAI and cutting speed for ductile material is right here. If this is roughly 95, it will come to roughly 1.25. 1.25. So the value of RAI is equal to 1.25 for ductile material for this given cutting speed. So we take the value of RAI out of this chart here, and then it sits here. Multiply it by the value of RI we have just computed up here, and this will result in a good estimation of the actual value of surface roughness for this given example. Well, now let's talk about the selection of cutting conditions. Indeed, one of the most important tasks in any machining operation is to properly select cutting conditions resulting in maximum profit, which could be achieved through maximum production rate or minimum unit cost criteria. In order to do that, there are four parameters that are more important than other ones in any machining operation, and those include depth of cut, feet, cutting speed, and also the utilization of cutting fluid. Well, indeed, depth of cut is decided by the geometry of the machining operation, of the geometry of the workpiece and machining operation. So we are not going to talk about it right now. And the type of the cutting fluid, also the selection of the cutting fluid, depends on the quality of the material and also the cutting tool. Let's talk about the selection of feed. The selection of feed, we just discussed how to compute the value of the feed in the finishing operation. In the roughing operation, it is not really important, so we've got to decide it on the basis of the rigidity of the machine tool, the power requirement, and the rigidity of the cutting tool itself. Only for the very last cut, we will compute the value of the feed as we discussed in the previous example. And how do we choose the cutting speed? Let's talk about cutting speed a little bit more in detail, which is a very important parameter in deciding the success of the machining process. Well, what I have highlighted up here is when we are going to decide about feed and cutting speed. Always feed first, speed second. How do we decide feed? Well, it's been briefly discussed in this slide here. That is, to determine feed, we've got to take into consideration the type of the tooling, what is the quality of the cutting tool that is used. For high speed steels, we will have different values of feed for carbide tools, ceramics and whatever, and of course it depends whether we are doing a roughing operation or finishing. For finishing operation, of course, there is a limit that must not be exceeded, as feed is the parameter that will significantly affect the quality of the surface finish. In the very last step, which is the finishing operation, we've got to actually compute the value of feed, and the feed should not be exceeded of the computed value if we are to achieve the desired surface finish. So this is briefly discussed. Let's move on to the next slide and talk further about selection of, say, cutting speed. As I said, when we are going to choose cutting speeds, generally we've got to consider one of the two criteria listed here: maximum production rate or minimum unit cost. Maximum production rate criteria should be selected when demand for the product is high, so we can make more profit out of selling more products. If this is the case, we are interested in maximum production rate. If this is not the case, the demand for the product is low, so we've got to make profit by lowering the cost of production and tooling. Then we go for the next criteria, that is minimum unit cost. Well, in this slide here we can see an equation that is used in order to compute the cycle time for producing 1 unit of the product, that is determined by TC, cycle time. And it has got 3 components. Those include TH, that is the time for loading and unloading, TM, that is the machining time, and also TT, that is the time for tool changing. Of course, we don't make use of a single tool in order to produce. We don't change the tool time for every production. Once a tool is changed, we can make use of the same cutting tool in order to produce a number of parts, and the number of parts are defined here by NP. Okay, the number of parts that can be produced after a tool change is defined by NP. Now let's take a look at this figure here. In this figure here we can see a diagram that is used in order, and in this we have got cutting speed in the horizontal axis increasing from left to right, and we've got TC in the vertical axis. In horizontal axis we've got cutting speed against TC, which is the cycle time in the horizontal axis, in the vertical axis. Well, regardless of the cutting speed, what cutting speed is, there is a fixed value for say loading and unloading of the part, which is this one. And then as cutting speed increases, as we discussed before, as cutting speed increases, the required time for machining, or TM, will decrease. So this curve is representing the required time for producing one piece of the product, and as cutting speed increases, the required time will decrease. And in this curve here is representing the tool changing time, and as we know, as cutting speed increases, then we are in need of more frequent tool changes because the tool life will decrease. As a result, as V increases, tool changing time will also increase exponentially. And putting all these components together, we can achieve the cycle time. Up here we've got a curve which is representing the time for TC, total time per piece. And how is this achieved? If we put at this value of maximum V, if we place the time components, those include from here to here we've got TT plus TM plus say TT. Then we end up in this point that is the minimum value of say TC. So what can be concluded is that when we are targeting maximum production rate, there is a certain value of V or cutting speed for which we achieve the minimum value of TC right here. How do we compute this value? Credit goes to Gilbert, who has defined this model, the model for computation of a cutting speed giving us maximum production rate. On the basis of what we discussed in the previous slide, we have this equation for computation of say TC, or cycle time for production of one piece of product. If we compute the value of NP and Tm and substitute these values into this equation, then we end up in this equation down here. How do we do this? NP, that is the number of parts to be produced by one cutting tool. How do we compute it? T represents tool life and Tm represents machining time in a turning operation. Equation for tool life can be computed from Taylor's tool life equation that we discussed in the previous lecture, and the equation for Tm, machining time in turning, is something that we discussed in lecture 5. By substituting the values of T computed from this equation and Tm from here into the equation of TC, then we end up in this equation down here. And we know that from the math units we have done before, we know that for computation of local maxima and minima, what we need to do is to take the first derivative of the equation and equate it to 0. So we take the first derivative of this equation with respect to cutting speed and equate it to 0, which leads to computation of this equation. And this is what Gilbert has done in 1950. You don't need to worry about all this computation. What you need to worry about is just how to use, what we need to worry about is how to use this equation which is in the frame, in order to compute the cutting speed giving us maximum production rate. Okay. And then if we want to compute the value of cutting speed giving us minimum production cost, we've got first to consider the equation giving us the unit cost as presented here. This equation here is telling us how we can compute the value of CC, that is the cost of production of one unit of the product. It has got a number of components. In this equation, CO represents the operator cost rate, TH, TM, and TT mean as we just described in the previous equation. CT is the cost of tooling, and everything else is already previously discussed. Now Gilbert has also done the same task for computation, for deriving the equation for cutting speed giving us minimum production cost, and it's just shown here in the frame. Again, how it is derived is explained here. You don't need to worry about what I have explained here. This is just for your information. However, the basic equation for computation of the unit cost is given. Then when we substitute the values of T, M, and also CT in the equation, it results in this equation. By taking the first derivative of this equation with respect to cutting speed, or V, and equating it to 0, this equation is concluded. What we need to worry about is how to utilize the equation in the frame in order to do the computations. And this will result in the lowest value of unit cost. So what is in this equation we can compute what is the cutting speed giving us minimum unit cost, which is derived in this equation. Okay, now let's do a couple of examples in order to see how we can utilize these equations to say compute the values of cutting speed for the given problems. Okay, in this problem what we have is a turning operation. In the turning operation we are making use of a high-speed steel cutting tool, and then Taylor's tool life equation values of N and C are given, as we can see here. The workpiece in the turning operation, the workpiece has got a certain diameter and length, and these are given here and here. This is the length, and 100 millimeter is the diameter of the workpiece to be cut. Feet or F is given, so we have got the value of L, we have got the value of D, we have got the value of F. Handling time or time for loading and unloading is also given, that is TH. And then tool changing time is given equal to 2 minutes, that is TT. And then the task of us is to compute a cutting speed for maximum production rate, that is maximum V, and also the cutting speed for minimum cost, that is V for minimum cost. How do we do this? We've got to make use of the equations that were introduced in the previous slides. This is the equation for maximum production rate of V. Of course, C is given, V is given, T is given, to changing time. If we substitute those values into this equation, we can easily compute the value of V for maximum production rate. And then by making use of the equation for minimum production, for cutting speed for minimum cost, then let's see if everything is given. C and N are given, of course. CO, which is the operator cost for machining. Let me see if this is given. Yep, it's given up here, $30 per hour. We've got to convert it into dollars per minute, of course, before it is used in this equation. And then CT is also given down here. It's $3 per cutting edge. If we substitute all these values into the equation, we can compute the cutting speed for minimum cost. And as you can see, the cutting speed giving us maximum production rate is greater than the cutting speed giving us minimum production cost. That's very obvious. And of course, when we are making use of say maximum V, then tool life will be less, and this will increase the cost of tooling. However, we make profit out of making more parts. When V is less, then tool life will be greater, so tooling cost will be less, and then we save the cost of tooling, which results in lowering the cost of production. Okay. And in problem 4, it's asking us to determine the hourly production rate and also cost per piece for the two cutting speeds computed in the previous example. In order to do this problem, what we need to do is to compute, to make use of the equations for, say, the equations for cycle time that we just introduced, as well as the equation for unit cost. So we've got this equation for cycle time and the bottom equation for unit cost. In order to do the problem, first we need to compute the value of machining time here by making use of the equation that we had in say one of the previous lectures. Let me see what equation number is. That is equation number 21.5. This is the equation 21.5. Equation 21.5. This one we had it in lecture 5, and this is equation 22.1. we had it in lecture 7. So we make use of the equation of TM, machining time for turning, taken out from lecture 5. We do the computation of TM, then we do the computation of tool life from this equation. Then we substitute the values into the equation for TC and CT and do the computation of cycle time for cycle time, the time that is needed in order to produce one part. On the basis of this, we can divide 60 minutes by the time that is needed to produce one part, giving us the production rate for maximum production rate criteria. And accordingly, we compute the unit cost for this criteria. So by utilizing this, we can produce 3.1 parts per hour when maximum production rate is used, and the cost of production of each unit is computed down here, $12.79 per piece. Now we repeat this for the minimum cost criteria, which is down here, and then we again compute the production rate for minimum cost criteria as well as unit cost for minimum cost criteria. And as you can see, these are both less than what we had for the previous case, because now we are not targeting maximum production rate, rather we are targeting lower cost of production. Okay. Well, I'm not going to talk about maximum optimum machining, optimum cutting speed in milling. However, I'm letting you know that there is a publication which I have actually published. It's a research which I completed in 1997. On the basis of that, I have published a paper which you can see it here, and in this table I have also developed a number of mathematical models for computation of the unit cost as well as unit time for milling operations. You can see the equations here. This is not for this unit, this is not, will not be included in the final exam, just for your information. In case you need to do the computation of the say machining parameters, optimum machining parameters for milling in the future, you can refer to this paper, and all the models can be found in this paper which I have just introduced. Okay, and I am leaving to you the rest of the lecture, which is a review of considerations, design considerations in order to lower the cost of machining in traditional machining operations. And that's all for today. Thank you very much for your attention.